Good morning, Gen Chem 2. I am so excited to share this next video with you. It is one of my favorite topics, and that is spontaneity. I know, doesn't that just sound fun? You know, you think about it and you think, oh man, this has got to be the best chemistry lecture ever. This is going to be fun. So let's take a second and actually just review a little bit of our thermochemistry. This is our last video in the sequence of our thermochemistry and our thermodynamics. And then we're going to do some sample problems on Zoom for this topic. So what we've looked at so far, we've learned about our enthalpy, and we've learned several ways to actually calculate that enthalpy. And coming from our table, our enthalpies of formation and our enthalpies of our reactions. Okay, that's awesome. And we also learned that sign matters. So if you've got a negative, your exothermic, and a positive in your endothermic, we're going to use those today. And then we also, our last video was this crazy term entropy. And we calculated that nice change in entropy. And this one was the opposite, actually. So we tend to go towards more disorder in the universe. That's positive for entropy. And then negative is you're confining something, you're restricting it, you're going towards more order if you're negative. So we actually have learned two different terms now when it comes to chemical processes and chemistry reactions. Let's learn the third term, which I think is probably one of the most important concepts we're going to learn. And that is really just a simple question. Is a reaction going to happen? All right, so let's write that down. So I love it. We just take for granted. We write our little reaction scheme on a sheet of paper and we just think we don't even think about it. We just assume it's going to happen. Well, how do you know? Is a reaction going to happen? Well, there's really two answers. The first one is my favorite. You go try it. Remember, reactions are up to Mother Nature. They're not up to you. We can tweak them. We can add energy. We can subtract energy. We can do all kinds of things to try to get a reaction to happen. But at the end of the day, if you just take two things and mix them, is a reaction going to happen? And then number two is something called spontaneous. Is that reaction spontaneous? And that is actually all about energy. And let's actually spell it right. Is that how you spell spontaneous? And so this second one then is something we can actually calculate. If a reaction is spontaneous, that means it's going to happen without your help. Without any external factors, without your help, if you take two things and mix them, is a reaction going to happen? If it is, that is a spontaneous process. And how do we calculate that? This is all due to energy. This is something called Gibbs free energy. And that is our term G. So, you know, on your table, you see a whole lot of values for that delta G. That is our Gibbs free energy. Okay, I love it. So let's review just really quick. What does spontaneous even mean? It means for us in chemistry, is a reaction going to happen? And will it happen without external factors, without your help? If you're sitting here and you've got a beaker of sodium chloride and a beaker of, water, and you mix them together, will a reaction happen without you helping? So let's put without help. All right, so we can actually calculate this, and it turns out that there are two main factors in if a reaction is spontaneous, and that is, you guessed it, enthalpy and entropy. I love it. So let's take a look at what it means for a reaction to be spontaneous in connection with our enthalpy. We're going to use some vocab here. If you look at a process in enthalpy that is exothermic, remember what that did with our energy. Okay, now we're physically going to calculate a number with our Gibbs free energy, and that number is going to help us figure out if this reaction is spontaneous. It is all about energy. So if you have a reaction that is exothermic, what's happening with our energy? For something that is exothermic, you're actually releasing energy. So if we mixed HCl and sodium hydroxide like we did in lab in calorimetry, heat flowed from that reaction to the surroundings. That was an exothermic process. We're going to add some more vocab to that. Anything that is exothermic is actually energetically favorable. That means it's going to favor our free energy. That is going to favor a spontaneous reaction. So that means the opposite is true. If a reaction takes energy, well, now it actually is endothermic, and it does not favor being spontaneous because you have to add energy into it. And if the point of a spontaneous reaction is that it happens without your help, well, being endothermic means that it needs energy. It's going to need your help. So it is not favored. So anytime you see an exothermic reaction, that is favored. Anytime you see an endothermic reaction, that is not favored. Okay, but wait a minute, Dr. Morty, we just learned in the last video, what if we take an ice cube and we set it out on the counter at room temperature? It's going to melt. That, my friends, is a spontaneous process. That ice cube is going to melt, and you didn't do anything to it. You just sat there and watched it. But yet that process is endothermic. Well, this is why we have a second term, okay? We don't have just exothermic, endothermic. We actually have to consider that last video, entropy as well. We've got two factors here. If our entropy goes toward more randomness or more disorder, more freedom, that is favored in the universe. Remember, it's almost the opposite. So when you've got something like an ice cube going from a nice rigid solid to a more free puddle of water, that is favored. That is going towards disorder. Okay? And then let's take our opposite. What if you take that water and you freeze it? Well, now your entropy is negative. You are going towards more order. That is the opposite of the way of the universe. So that is not favored. Okay, so let's say a couple things. All right, first of all, what if you go ahead and you calculate a reaction, which you know we're about to do. So how do you put all of this together and you figure out if something is spontaneous? Well, what if your delta H, what if your change in enthalpy is exothermic and your change in entropy is positive? You are going towards more freedom, right? Well, awesome. You've got a winner there. Both of these are favored. So that means your reaction is about to be spontaneous. You are favoring both of our terms. So this reaction will be spontaneous. Yay. Okay, well now the opposite is true, right? So what about the opposite? What if we have something that is endothermic and we're about to go towards more order? Well, now they're both not favored. So what does your gut tell you? That is one big no for spontaneous. Okay, now this seems pretty straightforward, right? You've got a nice exothermic reaction and you're going towards more freedom. Done. That is going to happen. You've got something that takes energy, it's endothermic, and you're making a crystal from a gas. Holy cow, that is not going to happen, right? So those two are fairly straightforward, but son of a motherless goat, what about the ones in the middle? All right, so what if your delta H is negative, but your delta S is also negative? Well, now we're going to have to calculate. All right, what about the other one? What if your delta H, or your enthalpy of your reaction, this time is endothermic, but your entropy is also a plus? So in other words, one is favored and one isn't favored. Well, now we're going to have to calculate. When we calculate, this is what we're going to calculate: Gibbs free energy. I'm going to give us two equations for Gibbs free energy and show you when we're going to apply both of them. Our first example, let's actually just apply this to a reaction. Let's start as a little bit of a review. Now, we've done this one in a couple of videos ago, so let's bring it back. Kind of like 90s fashion. Well, actually, maybe that shouldn't be brought back. Let's go ahead and just bring this back. Let's take this reaction and let's start and work our way through. And I'm going to make one big table. I'm going to start with delta H. I can't write this morning. And we're going to fill out those terms. And then we're going to calculate our delta S. So we'll do the delta when we calculate. And then I want you to go ahead and look at the table and let's calculate a delta G. I'm going to show us how to do that. So let's go ahead and add all of those numbers. It's going to be awesome. So I'm going to go ahead and read from my table, and I'm just going to put the units out here on the side because my table is just a little bit small. Remember your units for entropy. We've got two terms in here. The fact that it's joules and not kilojoules, that's going to be a big one. That's a common mistake right there. And check it out. This means we're going to have a temperature somewhere in there. And then our delta G, we are back to kilojoules per mole. All right, so grab your table. If you've got to hit pause on the video. Grab your table and let's start to write some numbers. All right, I've got and 0 for chlorine, right? That's an element. Okay. All right, let's look at our entropy. Let's look at our entropy for everything. Remember, there's no zeros in here. It's not possible, right? So don't just default and put a 0 here. It's never 0. Entropy is not 0. It's not really possible. You'd have to be at absolute 0 in temperature and stop all motion. And then you get into a whole theoretical physics discussion. All right, so then let's go ahead and grab that table and let's look at our new term. Let's look at that delta G. And I have minus 324. I've got minus 286. And then, oh, check it out. We're back to 0 at chlorine. I love it. All right, so let's start to do some math here then. All right, let's start with our enthalpy. Let's calculate the enthalpy of that reaction. Remember, that's products minus reactants. So let's go ahead and start writing that out. And is our reaction balanced? Yeah. All right, so let's take our products minus our reactants. We did this already in another video, but I just thought it would be a good refresh. And now what I get is a positive 92, right? That is endothermic. All right, let's just pause for a second. Let's add to that. If we have to add energy to that system, already, is this favored or not favored? This is not favored. So if we had to guess on just this one term alone, we would guess that this is not spontaneous because it's endothermic. But we don't have just one term. We have a second term. So let's go ahead and calculate our change in entropy. Whew, that's a tongue twister. Again, let's take our products minus our reactants. Okay. Okay, remember my units are up there. I just cheated a little bit. All right, so now when we calculated this one, what did we get? We got a positive 181.7. Okay. So this means that we are going toward more freedom or more disorder. So, let's add our new term to that. That is favored. So this is brilliant. This is one of those that we're caught in the middle. We're endothermic, which isn't favored, but we're going towards more freedom, which is favored. So we can't tell from this if our reaction is going to be spontaneous. So what we need to do is calculate. There are two ways to calculate. If you are at, and this is big, so if you are at 298K, that is what's on our table. That is our standard. Okay, that's why we have this little knot here. We are at standard room temperature. Then we can compare the delta G from our table, just like our enthalpy and entropy. We can do products minus reactants. All right, so let's try it. Let's take our products minus our reactants. And let's see what we've got. All right, we've got delta G. Let's take those products minus reactants. So grab your calculator again and let's take some numbers here. All right, my products are, I got to scroll up just a little bit. That minus 286. And 0 minus those reactants. So minus 324. All right, grab your calculator. This one we haven't done already, so I need to grab my calculator as well. Grab your calculator and let's try it. All right, we've got 286 minus 'I get a positive 38.3. Okay, does anybody else get that? We've got our reactants minus our products. All right, so what do these numbers mean then? All right, let's look at our sign. Just like the sign on enthalpy and entropy, our sign on delta G is going to tell us whether we're favored, not favored. That's for enthalpy or entropy. But the actual delta G tells us if something is spontaneous. If we have a positive, that means we are not energetically favorable. This is not spontaneous. If this number were negative, our reaction would be spontaneous. Remember, our Gibbs free energy is energy. So if you're releasing more energy into the universe, that is what's making that spontaneous. So if you do a calculation and you are getting to a negative, your reaction is spontaneous. I love it. So let's go all the way back up to the top. And let's take a look at that. How do you tell if a reaction is spontaneous? Well, you can try it. Again, Mother Nature is number one. Number two, if your Gibbs-free energy is negative, that is telling you that that reaction will be spontaneous. All right, let's pause before we do another problem. And let's do a nice big summary here. All right, if your delta G is negative, that is spontaneous, that means that reaction will happen. But let's add on here that there is no time associated with this. That is our next unit. That is unit 2. That is kinetics. So in other words, that reaction is spontaneous. It does not mean it's going to happen in 30 seconds or right now or in 0.1 milliseconds. It has no time associated with it. It just means it will happen. It can take 1 second, 1 hour, or 10,000 years. It just means it's going to happen. It doesn't mean in what time. All right, let's stop this video so it doesn't get too big, and then we're going to come right back on a part 2 and do one more problem. I love it.